So my name's Sam Boone. I'm a senior research fellow in tectonics and thermochronology at the University of Melbourne, where I spearhead the Melbourne Thermochronology Group. And today I'll be talking about how we can use thermochronology to investigate rift inception processes in East Africa. Okay. So what are low temperature thermochronometers? Well, they're like any other radiometric dating technique in that they're based off of the radioactive decay of a parent nuclide to some daughter product. But unlike, say, higher temperature geochronometers, say like uranium lead, that has a high closure temperature and therefore can be used to deduce information about, say, higher temperature geological processes like mineral crystallization, petrogenesis, high-grade metamorphism. Low temperature thermochronometers, instead, those systems remain open to much lower temperatures, meaning that the system remains open even as at the temperature regime that's common in the upper crust. And as such, we can then use it to deduce information about things like denudation and exhumation. So as an example, we'll look at the uranium, thorium, samarium, helium system, which is based on the decay of those parent nuclides to helium-4. And at high temperatures, there's so much energy in the system that the helium-4 particles instantly diffuse out of the crystal lattice. And only at lower temperatures do we just start to partially retain those daughter products. And we gradually retain more or a higher percentage of those radiogenic helium-4 nuclides as the sample cools to lower temperatures. We can then numerically model that behavior using the measured concentrations of parent and daughter nuclides in the crystal lattice, and then extract a time temperature history that is consistent with those data. And those time temperature histories can be integrated over tens or even hundreds of millions of years in certain cases. There's a number of thermochronometers, the three main families being argon-argon, fission track, and uranium, thorium, helium analyses. But when we're talking about low temperature thermochronometers, we're really talking about fission track and uranium, thorium, helium systems. And those are most commonly applied to the mineral apatite, although we can apply those to other minerals as well. And the temperature sensitivities of these systems correspond to temperatures that are common in the upper, say, 4 to 6 kilometers of the crust. And as I said before, this makes them very useful for trying to constrain the timing rates of near-surface tectonic processes. As such, people have long applied thermochronology in rift settings for quite a number of decades now. And in certain rare cases, these systems can record basically thermal events associated with the emplacement of plutonic bodies, such as dikes and sills, or heating due to hydrothermal fluids. But it turns out that these systems are so transitory in nature, these systems cool off so rapidly relative to geological timescales that only rocks that are directly adjacent to these heat sources actually record these thermal events. And if we look at the apatite fission track analyses across Kenya, we can see this quite clearly. So here's a geological map of Kenya. And there's been, the country records quite a significant history of rift-related magmatism since the Oligocene, where, and since that time, huge volumes of volcanics have been extruded across the nation. And yet, if we compare the distribution of Oligocene to recent volcanics and apatite fission track ages from the underlying basement, there's no real spatial correlation. And instead, the trend in fission track ages actually match the tectonic fabric of the country, with the oldest apatite fission track ages being preserved in the stable Tanzanian craton. And the kind of dominant thermal signature in the country is this late Cretaceous, early Paleogene cooling that we see in kind of orange and yellows here. And that seems to mirror the trend of a Cretaceous Paleogene rift called the Anza Rift that transects the country from the southeast to the northwest. And this is because in the vast majority of cases, thermochronometers record advection of mass and heat towards the surface due to erosion and exhumation. And in extensional settings, these can also record advection of mass and heat towards the surface in response to isostatic footwall uplifts related to basin bounding normal fault systems. And thermochronometers and geoscientists take advantage of this phenomenon by essentially using thermochronology to try to constrain the age of basins. And this is particularly handy when the oldest, earliest synrift sediments remain buried at depth. To do this, we would normally take a transect of samples, generally orthogonal to the major basin bounding fault system. We'd then acquire multiple different types of thermochronology data and then model these collectively to constrain a time integrated thermal evolution for that basement block. And in this example from a paper we published in 2018, looking at the northern Turkana Basin in northern Kenya, we then used a recorded pronounced period of mid-Miocene, about 13 million years, to recent period of rapid cooling and we argued that this was measuring essentially the onset of uplift of the rift margin, and therefore was a proxy for the age of the basin being mid-Miocene. So a lot of my work to date, and colleagues of mine working together, we've tried to use these sorts of techniques to try to constrain the very earliest history of rift initiation in East Africa. To do this, we focused on the Turkana Depression of northern Kenya and southern Ethiopia. And this is because it's long been known that this region hosts the oldest rift-related magmatism in the East African rift system, in the form of the Amaragamo basalts, shown in blue and green at the top of this geological map, which started being extruded under the surface of East Africa around 45 million years ago. And since the work of Chris Morley and others in the 90s and after, it's also been suggested that this area hosts the oldest rift basins as well. Namely, the Lokichar Basin has often been put forward as a candidate for the oldest basin in the entire rift system. This half-graben in certain places hosts as much as 7 kilometers of synrift strata, so it's quite a deep basin. And a well of the Loprot 1 well, which penetrated some of the synrift sediment along the flexural margin of the basin, penetrated Oligocene synrift strata, but actually the deepest parts of the basin have never been penetrated. So Chris and others suggested that this basin is very likely much significantly older, possibly early Oligocene, even Eocene. So in 2019, Chris, myself, and other colleagues published a paper where we used thermochronology to essentially constrain the thermal evolution of the footwall of the main basin bounding Lokichar fault. And the thermal history modeling of this data basically revealed a spatial thermal signature that's diagnostic of isostatic footwall uplift of basin margins, whereby samples more distal, further away from the fault trace, shown in red and orange here in that time temperature plot at the top, have this protracted late Cretaceous to recent cooling history consistent with the dominant kind of background signal across Kenya and southern Ethiopia. Whereas samples in the proximal footwall, within a kilometer or two of the Lokichar fault trace, record really rapid, pronounced cooling to near surface temperatures that began somewhere between about 45 and 35 million years ago, which is consistent with this basin being as old as possibly middle to late Eocene, and confirming that this is the oldest basin in the rift system that we know about thus far. So synthesizing those results with lots of other published studies constraining the age of both rift-related volcanism and basin formation throughout the East African rift, quite an interesting spatiotemporal chronology of rift evolution is revealed, whereby rifting began in discrete nucleation zones, the first being in the Turkana Depression around 45 million years ago, certainly with rift-related volcanism, and probably soon after basin formation. And then you had a slightly younger, or quite a bit younger nucleation zone in the Afar region, as well as the Rukwa rifts down in the south. And only later that rifting kind of propagated latitudinally, both north and south from these nucleation zones, eventually forming a nearly continuous rift system by the Pliocene. Interestingly, in the late Paleogene, when we think basin formation started in Turkana, we also see that there's documented reactivation of older Cretaceous basins, both in the South Sudanese rifts to the northwest of Turkana and in parts of the Anza Rift to the southeast, suggesting that this tensile stress regime was actually regional and not limited just to the immediate Turkana region. So why did rifting nucleate kind of in the Turkana Depression area, kind of in the middle of Africa? Well, lots of people point to the fact that there's quite a significant tectonic inheritance story in this part of East Africa, namely that a series of Cretaceous early Paleogene rifts attenuated the lithosphere and crust in this region, and it's thought that the Anza Rift and the South Sudanese rifts once connected through this Turkana region. Work from Sleep and Ebinger and others suggested that this kind of pre-attenuated crust in northern Kenya could have acted to channel upwelling asthenospheric material once with the arrival of the East African superplume, as it's sometimes referred to, which would have then further thermomechanically weakened the lithosphere there. And people like Vital and Legal have suggested that pre-existing lithospheric heterogeneities from this earlier rifting phase also could have been reactivated and helped, I guess, focus brittle strain.
You have 10 minutes now.
Thank you. And work from Sasha and others have also shown from numerical and analog modeling that such a pre-attenuated crust could also explain why brittle strain is so widely distributed in this part of the rift compared to the relatively narrow rift systems in Ethiopia and Kenya to the north and south. Okay, but what was driving rifting in the Paleogene? Well, modern rifting by many is thought to be driven by essentially gravitational collapse of the so-called African superswell, this area of anomalously high topography found throughout East Africa, Southern Arabia, and South Africa, or Southern Africa rather. And this high topography has developed partially due to a dynamic topographic component due to plume impingement beneath East Africa, as well as the buildup of significant thicknesses of rift-related volcanism in the region. Work by Sarah Stamps and colleagues have shown that the deviatoric stresses from this gravitational potential energy of this high topography alone is sufficient to continue modern day rifting or continue extension today. And they also showed that the predicted stress regime from the gravitational collapse of this region alone also very closely matches modern kinematics of the rift. But interestingly, they also found that the present day stresses are insufficient to rupture cold thick lithosphere, meaning that at the onset of rifting, some other mechanism, at least in part, had to be operating in order for the rift to initiate. Interestingly, there's no real evidence for high scale topography in the region prior to the Miocene, possibly latest Oligocene. And there's actually no evidence of the Turkana Depression ever having high topography anytime during the Cenozoic. So these lines of reasoning together suggest that we might need to start looking towards lithospheric stress as playing a larger role at the earliest onset of East African rifting. Others have shown, primarily through geophysical data in the Atlantic and Indian Oceans, that there's a major plate reorganization in the Middle Eocene. And we can see that here also in this plate tectonic model from Zahirovic et al. 2022, where at around 44 million years or so, we see quite an abrupt change in plate kinematics for India relative to Africa. So I'll leave it there. Before I go, I just wanted to plug the fact that Maria Laura and I and some other colleagues are preparing a huge synthesis of all of the published, as well as almost 1,000 unpublished fission track and helium results from across the entire Afro-Arabian rift system. This is fairly advanced preparation, so we'll hopefully be submitting that in the next few months or so. And we're going to make all of this data publicly available via the Oz Geochem platform, which you're seeing a video from here, which is an open source, open access geospatial data repository that anyone in the world can use. But in addition to allowing, to giving essentially a tool which people can make their data publicly available, it's also a 4D geospatial analytical tool. So you can investigate your data on the fly in their geospatial context. You can do things like do interpolations of different variables, I suppose. But quite exciting is that recently we've we collaborated with the Earthbite group from the University of Sydney and integrated G plates within the system, so people can quite readily project their data and samples back in time, and then you can analyze your data in their paleo geospatial context, which is quite powerful. So I encourage you to go check it out, add your data, use it. It's entirely free. And I think I'll leave it there. If you want to find out more about my work or my research group's work, please check out our website at melbournethermochronology.com. And I'll leave it there. Thank you very much.
Excellent. Thanks for this fascinating talk.
Thanks, Sasha.
We have time for 1 or 2 questions. If you have one, just raise your hand or type a question in the chat. I don't see a question so far. Derek, did you have a question?
Yes, yeah. That was a fabulous talk, Samuel, and the new data looks great. I had a question about your map showing the sort of interpreted age of the onset of rifting from thermochronology. How much do you think that's influenced by preservation of sort of the paleo surface? So, for example, I was thinking of more the Ethiopian rift, where most of the area outside of the rift is covered by the Oligocene flood basalt province. I mean, do you think it's possible that you've got rift below that from early Oligocene or Eocene that you just can't access at all in terms of outcrop, in order to date?
That's a good question. Quite possibly. I mean, I know there's, I'm blanking on the name at the moment, but there's some more kind of northwest, southeast trending basins to the west of the main Ethiopian rift that clearly have an older history that were then later reactivated. And there's parts of Western Turkana even where seismic data has revealed quite large basins at depth, but there's no well data to penetrating them. And I imagine that some of the best seismic lines are still proprietary, so we're not actually getting a good glimpse of what those basins really look like anyhow. So you might very well be right there. It's quite possible.